This seems like an absolutely stupid title for a section in a course that happens after calculus, but how to count? I want to count big things. That's the issue here. So, how many license plates are there in the state of Pennsylvania? How many ways are there to get a hand of bridge? Anybody play cards? Hand of poker. How many different poker hands are there? Lots, right? How do I figure this out? How many lottery tickets are there for the Powerball? Possible. I mean, there's one that's going to win, but how many possible ways can I do that? The most direct version of this, fundamental counting principle. The multiplication rule. If there are n1 ways to do task 1 and 2 ways to do task 2, ... and k ways to do task k, and I need to do all of the tasks, that I multiply together all of the options. If they are independent tasks. I'll make the definition of what it means to be independent a little more precise later on. But the overarching statement here, if I have a bunch of different ways to do a bunch of different things, I know the number of ways to do each of the things, I can just multiply them together. How many license plates are there in the state of Pennsylvania? If I ignore for a moment custom plates, let's just think about the plates issued by the DMV. What's a Pennsylvania license plate look like? They changed them fairly recently. What do the new plates look like? Blue letters. They're white with blue letters. Before they had blue letters, but they also had a yellow stripe and a blue stripe, but they still had a white background. What else did they do? They changed the image. Behind the letters and numbers is a Liberty Bell. It used to be that the letters were separated from the numbers by a little icon. Anybody know what that icon was? The motto, the slogan for the state of Pennsylvania, the blank state. It was a little keystone. But they didn't change the pattern of letters and numbers. A Pennsylvania license plate is 3 letters, then 4 digits. Let's make an assumption. You can have any letter in the letter spot and any digit in a digit spot. And there's no requirement to put one with another. Okay. Then how many possible license plates could I come up with? I get to choose 7 things. How many choices are there for the first spot? 26. That's the number of ways to do task 1. Pick a letter and put it here. Task 2. Task 3. Task 4. Aha, I'm on the digits now. And the same with 5, 6, and 7. There you go. That's the total number of possible license plates in the state of Pennsylvania. This is a not insignificant number. How big is this? Grab your calculators, give me a number. $175,760,000. That is enough license plates to give every single man, woman, and child in the state of Pennsylvania a license plate stapled to their butts. The most recent license plate I have seen started with the letter N. When I moved to Pennsylvania, they just changed the license plates. This is 1992. My license plate started with an A. They took it away from me eventually when I got rid of that car. But we're going to be a while before we have to wrap back around and start using letters again. Questions? How long is a phone number? 10 digits, right? That was not always the case. Your parents, when they dialed a phone number, if they dialed a local phone number, they didn't have to dial the area code. You only had to dial 7 digits. But as phone numbers got denser and denser, we needed to add more digits to be able to tell everything apart, even if I wanted to call something locally. So really, a phone number is an area code, an exchange, and an extension. If you are calling someone on the Seton Hill campus, it is either 838 or 830 for an exchange. Seton Hill owns those 2 exchanges. And that means Seton Hill owns all the phone numbers that start with 724-830 and 724-838. If you go into a cell phone company and you say, I want to buy a phone, and you've never had a phone before, they give you a number because they bought an exchange. They have numbers they can sell, but they had to buy a whole exchange to do it. Now, when the phone company started, they had some rules on area codes. The first digit of an area code could not be a 0 or a 1. The middle digit of an area code had to be a 0 or a 1. Clearly, we changed that, right? 724. In the exchange, neither of the first 2 digits could be a 0 or a 1. But any other digit that we have not specified could be anything we want. Under this setup, how many phone numbers were available? Again, this is a matter of putting in the number of options we have in each slot and then multiplying. I have 8 options here. I have 2 options here. I have 10 options here. 8, 8, 10, and a bunch more 10s. Blake, what number do I come up with?
I think it's 1,024,000,000.
And that's just for the United States. But clearly, that's a problem. I mean, we live right now, Seton Hill resides in the area code 724. That means they changed this rule at some point. As a matter of fact, they got rid of the rule that you had to have a 0 or a 1 in the middle of the area code. And they got rid of the rule that you had to have a 0 or a 1, no 0 or 1 in the exchange. So you can now have an exchange that has a middle digit of a 0 or a 1. If I do that, which I believe was done in the late 80s, the Telecom Act of 19, I've forgotten what year it was. You can look it up. Well, now I end up with 6,400,000,000 possible phone numbers just in the United States. But in order for me to buy a set of phone numbers, I have to buy an exchange, which means I buy phone numbers in lots of 10,000. The more people that want to own a particular exchange, I want to own a hotel. I don't want to have half the numbers be 625 and the other half of the numbers be 626. It'd be much easier if I owned the whole exchange and anybody that dials 625 comes to my hotel. It would work. But then what if I don't have 10,000 rooms? What do I do with the rest of the numbers? I sit on them. Or I sell them to someone else. But that would dilute the idea of me having the number. By the way, exchanges used to not be numbers at all. I am showing my age again. What happens when you dial a phone number? What do you hear in your ear? Before that, when you're dialing, you hear the numbers as tones. And they're different numbers. They're different sounds for different numbers. Why? Because the tone tells me which number is being dialed. Before that, old phones with dials on them used to actually physically click. A 0 clicked 10 times. A 9 clicked 9 times. A 1 clicked 1 time. And the relay on the other end of the phone would hear the clicks and know where to stop the connection. Before that, there used to be a human being sitting there who would literally plug your phone line into the number it was supposed to go to. They'd plug in to the extension at the exchange desk. So you'd have 6 or 7 people in a row with a bank of 10,000 boxes in front of them. They called your exchange and they said, which number do you want to connect to? You told them, I want to connect to extension 5,000. They find box 5,000 and plug you in. There was a song about this. The 6th Pennsylvania extension, Pennsylvania 6 5000. It's a rather famous song. You should look it up. But that's literally why it's called an exchange. You would call the exchange and they would plug in the right extension. The critical piece to me on all of this is actually that this goes all the way back to chapter 1. This connects to logic. I want to do task 1 and task 2 and task 3. I'm multiplying. Chapter 1, that's our logic term. We did this in chapter 2 with Cartesian products, right? Something from set 1 and something from set 2 made ordered pairs. Well, if I can do it for the word and, I can do it for other rules. So I'm going to go with the same setup as before. There's N1 ways to do task 1 and N2 ways to do task 2, Ni ways to do task I, 1 to K. Then I want to do one task, just one. Not all the tasks, just any one of them. But like I made the comment about independent before, I need to make this comment about exclusive here. There's not one thing that will do more than one task. I can do the laundry, or I can mop the floor, or I can read one of these books, or I can, right? But there's not one way to do multiple tasks. I go to a restaurant for lunch. And they've got quite a bizarre menu. There are 23 different entrees available, 10 different sandwiches available, 5 platters, and 15 salads. Pick one. What are you having for lunch? How many choices do you have? Just add them all up. Hey, wait a minute. Again, I've seen this before. When we were counting things back in chapter 2, we were counting sets, right? The number of things in a set. What set symbol goes with the word or? I didn't tell you we're allowed to forget any of this crap. The U shape, that union shape. Right? And we were counting things. What symbol went with how many for a set? Chapter 2, section 1, 2, and 5. The word I'm looking for is cardinality. The cardinality of a set. There was a symbol for cardinality. It was the absolute value bars around the set. The number of things in this set or that set we added, right? But I could only use this formula because of that word. Back in chapter 2, what Venn diagram picture went with this? What does it mean for my sets to be exclusive? They don't overlap. They don't overlap. In set terms, we had disjoint sets. So the obvious question is, what do I do if they do overlap? We did this back in chapter 2. I guarantee you I'm not bringing up something you've never seen before. You just might not remember. That's a whole different ball of wax.
Is that in the case of an exclusive?
No, this is when they are exclusive. This is where they're not exclusive. So maybe one of the tasks does more than one thing, right? But how do I count? If I just want to count the number of things in the union here. Colin? The overlap, right? I got to take away the overlap because I counted it for the first circle and then I counted it again when I counted the second circle. So I have to subtract the intersection, which is our overlap. So I include everything once, but then the stuff I count twice, I have to exclude because I double counted it. This idea, surprising, I hope nobody, is called the inclusion-exclusion principle. And it can be extended to more sets. But when you extend it to more sets, it gets more complicated. Anything that is counted an odd number of times needs to be kept. Anything that's counted an even number of times needs to be thrown out. So stuff you count once, you count everything once. But that means you counted stuff twice. So you got to throw it out once for every time it was counted twice. But if you counted something 3 times, then you counted it 3 times, you threw it out 3 times, that means it's not there anymore. Three sets, right? A, B, C. So I take the number of things in A and the number of things in B and the number of things in C. But this piece right here, this is counted twice. It was counted in A and in B. So I have to subtract the stuff that was counted in A and B. I counted it twice. I have to do the same thing for A and C. I have to do the same thing for B and C. You with me so far? Helps if I can see the whole freaking picture. Now, the stuff that's on the outside in set B, this piece right here, it got counted once and it never got thrown away. This piece got counted once, never got thrown away. This piece got counted once, never got thrown away. This piece got counted twice and then thrown out once, so that's good. This piece got counted twice and thrown out once, that's good. This piece got counted twice and thrown out once, that's good. I counted that for A, for B, and for C. I threw it out for AB. I threw it out for BC. I threw it out for AC. I didn't count this part. I put it in 3 times, I took it out 3 times. It's not in there anymore. So I have to add back in something with 3 sets. When it's an even number of things, we subtract. When it's an odd number of things, we add. You do this for as many sets as you want. The Venn diagram gets uglier. We looked at Venn diagrams that were ugly, so I'm not going to do those Venn diagrams again. But that's the way to pick up the missing pieces. Why? Seriously, who gives a shit? Here's an example. I am making this question up to be relatively simple. I know it doesn't sound like it. I want you to write me a bit string. That's a string of 1s and 0s. 8 bits long. So 1 byte's worth of information. How many possible bit strings of length 8 start with a 1? How many start with a 1? How many end with 00? How many do both? How many do either? That last question is important. Start with a 1 or end with a 00. Only way to answer that is to use this inclusion-exclusion idea. I'm going to count. Here's condition 1. There are my 8 bits. No, there are my 8 bits. How many choices for the first bit? 1. It's got to start with a 1. The rest of them? So how many total? 2 to the 7th. 128. How many of them end with a 00? Because these two only have 1 choice each, but everything else has 2 choices. How many do both? because the first one will be a 1. And then 2 choices, 2 choices, 2 choices, 2 choices, 2 choices, and then a 0 and a 0, 1 choice each. So here's the idea. If I want to know how many do one or the other, I take the 128 and I add the 64. But that means I double counted all of these. Every bit string in this pile is in both of those. Since I double counted them, I have to pull one set back out. So I can add, I can subtract, I can multiply. Makes sense, right? Question. So let's step this up a bit. Suppose I have a task that can be done in n ways. But for each way that I do it, there are a certain number of ways that are all equivalent. We'll call that D. Then there are n over D distinct ways to do the task. Now this sounds bonkers. What do you mean functionally equivalent ways? I have a round table with 3 seats. I have 3 people. They get to take seats at the table. All the seats are exactly the same. How many of these arrangements are possible? And how many of them involve people sitting with different people to their right or left? So let's think about sitting people at this table. Which person do you want to sit down first? The 12 o'clock person, the 4 o'clock person, or the 8 o'clock person? Okay, so how many choices do I have to put a person here? And then how many choices will I have at the 4 o'clock spot? And then I'll have, so there are a total of 6 choices of seating. Yes? So let's make a triangle. who's going to sit at the 12 o'clock spot? Person A is. So that means at the 4 o'clock spot, it's either person B or person C, yes? If I put person B here, then I'm stuck putting C there. Consider this from person A's perspective. From person A's perspective, person A has B on their right hand and C on their left hand. But what if I put person B at the 12 o'clock spot, person C at the 4 o'clock spot, and person A at the 8 o'clock spot? Consider this from A's position. Is it any different?
It's the same.
Isn't that the same too? But that is different. Now, from person A's perspective, C and B have switched sides. And if I do the same thing I did here, I see that 3 of these arrangements are functionally equivalent, aren't they? And so I take 6 and I divide by 3 and I get 2 different options. Option 1, option 2. By the way, in other mathematical courses, we would call these orientation preserving and orientation reversing ideas. That's related to handedness, whether something is right-handed or left-handed. If you have a glove that has a clear palm and a clear back, it's handed, right? It'll go on your right hand, but not your left hand. But you could make it go on your left hand. How? But if I rotate it, then the back isn't in the same place, is it? My thumb's not going to be in the same place. Remember, there's a clear palm and a clear back. If I rotate it, my thumb doesn't go in. I got to turn it inside. Put your fingers together, roll it off with one hand and onto the other hand. Then the palm is still on the palm, and the back is still on the back, and the fingers go in the right direction. But the inside is now the outside. I reversed in and out. Calc 3 talks about orientation in a lot more detail. If you want more on orientation and freaky things, look up a guy by the name of Mobius and his band, not music. How did I know that those were the only 6 options available to me? I mean, we counted them, but how did I know that those were the options? Because that's actually a really different statement. We enumerated, we counted these things. We didn't actually write them all down, did we? I didn't write down all 175,760,000 license plates. That had better things to do with my time, right? But if I want an explicit list, I should know how to make it. The general idea here is something called a tree diagram. In probability and statistics courses, you'll see this when we talk about conditional probability. In a lot of decision analytics courses, the same sort of thing gets called a decision tree. Let's think about codes. I'm going to give you a really simple request. I need a 3-digit number. Each number is a 1, a 2, or a 3. How many options are there? Right. "27 different possible options. What are they?" I'm going to need to write these out carefully to make sure I don't repeat stuff, yes? So let's think about this in order. I start with an empty 3-digit number. And then I put down the first digit. There are 3 choices. I then put down the second digit. There are 3 choices for each of these. See my branching? Thus a tree diagram. And if I do one more digit, and so on, what I can do is start at the left, for lack of a better term, at the root of my tree, and follow a branch. Follow the pattern. And if I go all the way across the top, I'll get 1, 1, 1. Up, 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 up. Middle is going to give me 1, 1, 2. And then I'm going to get 1, 1, 3. And then I'm going to get 1, 2, 1, and 1, 2, 2, and 1, 2, 3. And then I'm going to get 1, 3, 1, and 1, 3, 2, and 1, 3, 3, right? And if you think about this as if you were counting in base 4, then you'd roll over the 16s bit. This digit would become a 2. And you get 2, 1, 1, 2, 1, 2, 1, 3. Roll it over. 2, 2, 1, 2, 2. Aha. And this is a fashion by which I can show all the options, not just how many there are. If I told you you weren't allowed to repeat a digit, this would be a lot smaller of an option, wouldn't it? Three-digit number. Each digit is 1 or 2 or 3. No repetition. How many options are there this time? Three options, but then you've used a number, so you only have 2 options. Then you've used a number, you only have 1 option. And then I end up with, helps you write down the right numbers. 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. Replace the 1, the 2, and the 3 with A, B, and C, and you've got my rotations for the table. Questions? I was able to use the multiplication principle to know how many I was going to have before I started, because these were independent choices. But the idea of independent isn't very precise here. So I'd like to try and clarify that. My choices are independent if which choice I make does not affect how many choices are possible after that. So let's suppose for a moment that I'm going to change my 3-digit code ID. You're allowed to repeat numbers, but you're not allowed to have 2 odd digits in a row. This is suddenly a set of dependent choices, isn't it? I pick my first digit. What's allowed for the second digit? Depends on what I chose for the first digit. What's allowed here? And only 2, but here, what's allowed here? The number of branches just changed at that level. A dependent set of choices, not independent set. Now, what's available in the next spot? What's available here? I'm allowed to repeat digits, right? I can have even digits in a row, so I can do 1 or 2 or 3 here. But here, I can only do a 2. And here, I can only do a 2. Here, I can do a 1 or a 2 or a 3. But do you see how the choice I made changes the number of things that are available in the following steps? That's what independent in counting terms means. Much more on that when we start talking about probability and prob and stats as we move forward. I will see you all on Friday. Have a wonderful rest of your day. One of my favorite versions of this is how many games get played in the World Series or in the Stanley Cup. You have to win this many out of how many games are going to get played.